This video presents APPL, Adaptive Planner Parameter Learning, from the Learning Agents Research Group at UT Austin. In contrast to learning a conventional end-to-end motion policy that directly issues raw actions on the real world, APPL treats a classical motion planner as part of the environment and takes actions in the planner's parameter space. In this work, we present 4 individual APPL methods, from demonstration, interventions, evaluative feedback, and reinforcement, which are also combined to form a cycle of learning scheme to continually improve navigation across different deployments. A parameter policy is trained using APPL-R in the simulated benchmark autonomous robot navigation dataset. BARN is composed of 300 navigation environments randomly generated by cellular automata and covers a variety of navigation difficulties. In the first real-world deployment environment, APPL-R1 is able to accelerate in the relatively open space, while the DWA planner with static default parameters drives unnecessarily slowly. In the second deployment environment, after quickly traversing the open space, APPL-R1 suffers at the narrow entrance and executes recovery behavior by rotating in place. A human user who is familiar with teleoperation is able to demonstrate desirable navigation behavior using a joystick. APPL-D segments the demonstration into 2 contexts using Bayesian change point detection, finds one set of parameters for each context using behavior cloning, and learns the context predictor to select appropriate parameters with a neural network. APPL-D is able to quickly and smoothly navigate through environment 2. In the third deployment environment, APPL-D gets stuck multiple times in the narrow corridor and executes recovery behavior by driving backward. Since APPL-D is able to successfully navigate at most places, a second human user chooses to intervene only when the robot does not perform well. The user stops the robot, rewinds it to a place where the suboptimal behavior started, and gives a teleoperated intervention. This intervention adds a new context, and a new set of parameters is learned for this context with behavior cloning. In conjunction with the first 2 contexts and the first 2 set of parameters learned through APPL-D, APPL-I is able to drive fast in open space, smoothly negotiate through the narrow entrance, and slowly but confidently progress in the narrow corridor. In the fourth deployment environment, APPL-I sometimes generates unsmooth motion and sometimes executes recovery behavior. While user 3 is not comfortable with taking full control of a moving robot with a joystick, he is still able to give evaluative feedback on how the robot performs by pressing 2 buttons, one for good job and one for bad job. Using this less demanding human interaction modality than teleoperated demonstration and interventions, the robot is also able to learn how to select appropriate planner parameters to achieve the best expected evaluative feedback from the human user, and therefore keep improving navigation performance in this complicated obstacle course. To close the cycle, we initialize with APPL-R1, explore with the learned APPL-D, APPL-I, and APPL-E in the BARN dataset, and learn a better APPL-R2 policy. While exploration with APPL-D, APPL-I, and APPL-E learned from different human interaction modalities in the real world can help improve navigation performance in the simulated BARN dataset, we further show improved navigation in the real world with APPL-R2 compared to navigation with APPL-R1. Initialized from APPL-R1, APPL-R2 incorporates all human interactions within this cycle into the parameter policy. As shown in the video, APPL-R2 is able to quickly and smoothly navigate through all different regions of this complicated obstacle course and achieves a much smaller traversal time compared with APPL-R1 learned only through random exploration in BARN. When facing normal deployment environments where the robot suffers from failure or suboptimal behaviors, users can choose from the 3 interaction modalities: demonstration, interventions, and evaluative feedback, and then teach the robot to improve navigation performance, kickstarts another cycle of learning, and incorporates human interactions within this new cycle into a new APPL-R policy.